Welcome to Web Handling. My name is Dave Roysam. I am very excited to begin a new series on things you should know. In this first clip, we will talk about what coders need to know about their nearest customer, the winder. For it does no good to code a brilliant product that is easy and economical to make and that the end-use customer loves if you can't wind it. The number one thing that coders need to know about winders is that the number two thing that coders need to know about winders is almost important, and that is I hope I've made the case that there are two very important things that every coder needs to know about winders. Thank you so much for your attention. Any questions? I hope that I've gotten your attention. You need to pay attention because some coded product cannot be wound in any useful sense of the word. Yes, you can design and make unwindable products. Unwindable in three ways. The worst, which is uncommon, is if it can't be wound at all. The next case is where the roll can't be wound to useful roll diameters or widths given your winding machine and your winding machine settings, or perhaps any winding machine or settings. The final case is the most common. That is, it can be wound to desired sizes, but the internal rejection or customer complaints are unprofitably high, even with the best winder and best settings. The word profile is very useful. It simply means the variation of some property across the width of the web. Here, we will be talking about a thickness-related property, such as bulk, caliper gauge, thickness, density, and so on. Here, we will be talking about total thickness, which is the sum of base web thickness plus coding thickness. The winder, it turns out, does not care where the thickness profile variation is coming from, even if the troubleshooter must. If we are to wind without debilitating defects, the thickness profile must not exceed a certain amount. While that threshold of pain varies with the detail of the situation, the range is remarkably similar across a variety of chemistries and wound roll sizes. Roughly speaking, at a 1% variation, you will have few problems, and at 10% variation, you will have few customers. As I said, this range depends on details. With nonwovens and oscillated blown film, you can take a bit more. However, with metal foil, you can't take anywhere near that much. Most common materials, however, such as film and paper and textile and tissue, are mostly in that 1 to 10% range. Let's please try and avoid going down the rabbit hole whether this threshold is 2% or 6% variation, or whether the percent is peak to peak 1 sigma or 2 sigma measured in the lab or on the scanner, or whether your chemistry or winder might make more. Let's stay focused on the big picture. In general, the total thickness variation across the web can only be around a few percent, else you risk more and more of certain winding defects. Half-century-old literature mentions this range, and everything we've learned since comes roughly into that 1 to 10% range. Whether you can measure or control to that level is totally besides the point. The wound roll will judge you not upon your effort, but only on the result. So, which specific winding defects are risked with excessive variation? Well, here we break the list up into two categories, both of which are very large and very serious. The first category is those defects caused directly by winding materials with excessive variation. In other words, variation is a necessary and sufficient parameter even if there are also other factors. This list includes bagginess that is caused by stretching and yielding the web over gauge bands, by far the most common type, but not webs that are formed baggy. We will have more to say about this in the next slide. Other defects that result from excessive thickness variation includes corrugations, starring on one side but not another, and many or most wrinkles that are produced on the wound roll itself. However, those defects that are made worse with thickness profile variation includes nearly every tight defect, and nearly every loose defect, and most taper defects. In sum, quite a long and serious list. Way too much to include here. But those who have taken my advanced winding portion of my Web 101 training will have seen these details. In short, the winder controls the average stress, while thickness variation controls the range of stresses across the wound roll. It is these stresses and strains that cause these defects. Let's take a much deeper dive into one of the best studied of the winding defects. That is bagginess caused by the winding of materials with excessive thickness variation. We can begin with 50-year-old observations and check them with a simple back-of-the-envelope calculation. The sizes of the bumps that might cause bagginess could be very, very small. However, we don't need to take the word of long-dead authors or trust a simple calculation. An entire PhD thesis has been written on this subject. Dr. Cecilia Land, one of the several students I've mentored over the years, found that the range of thickness variation that could cause a problem on paper is, wait for it, a few percent. I have done work on foil laminates where far smaller variations caused bagginess. Even though film is tougher, the dead soft foil sandwiched between stretched permanently on tiny gauge bands. So, if gauge variation must be minimized to minimize winding defects, the obvious next step would be for QA to measure and screen rolls based on thickness variation. However, direct measurement challenges are daunting. Consider trying to resolve the variation of 1% on a web that is 1 mil or 25 microns thick. The result is you would need to be able to resolve thickness to within a few millionths of an inch. Lab instruments are seldom that good. Scanners are even far worse. Recall that the winder doesn't care whether you can measure, much less control variation to millionths of an inch. as with your end-use customer. The next customer in the process, the winder, will make its own conclusions about how level your product is. So, if lab tests aren't good enough and scanners far from good enough to detect, much less protect your customer from troubles, is there another way? Yes, and we've known about it for decades, and it works for most paper grades and many film grades. That is, the best roll hardness instruments, because they sample hundreds of layers at a hit. This is not the same as averaging 100 noisy scanner measurements. This is an integration process which is inherently numerically much better. Groundbreaking work by Amy Tour of Avery Dennison shows us how, in many cases, that you or your customer can screen rolls before they are mounted on an unwind or even shipped. Indeed, you might not even need to take them out of the wrapper. This work deserves and requires far more explanation than I can give here, so I urge you to read her iWeb paper or her Converting Quarterly article on this subject. Alternatively, you can see my YouTube summary on this subject in my Baggy Web series, or go to my Web 101 school. I will mention one last important concept, in that the winder also has a role in all of these issues, so I don't want to minimize that. Indeed, Amy shows how to account both manufacturing and winding at the same time. Yes, we always knew that thickness variation was risky. Yes, we always knew that winding gauge variation materials more tightly than you need increases the risk. To state the winder's role simply, you want to wind as loose as you can for any of these issues, not just bagginess. As I teach in Web 101, that means any and all of your TNT knobs need to be turned down to the extent possible, and then some. Before we close, I would like to at least briefly mention that among the many details that matter is not just magnitude, but also shape of the profile. On a broad scale, you might have taper, smiles, or frowns, or some combination, such as a tipped frown. If we hold magnitude constant, we find that some shapes are worse than others. With regard to bagginess, for example, frowns might be worse than smiles, because most customers can tolerate a bit of edge bagginess more than they can a bit of center bagginess. At a fine scale, we might see ridges, valleys, or steps. Valleys tend to be the least problematic because the web will simply bridge over them. Ridges, on the other hand, will cause vivid baggy lanes at the same magnitude of variation. Steps, on the other hand, are worst for corrugations, a very common defect seen on most thin materials. All of the shapes, excepting the valley, also risk wound roll wrinkles. Thank you so very much for allowing me to share this design for manufacturability summary. These are just some of the things that coders and winders both need to know. I hope I've made the case that even tiny variations in thickness across the width of a machine can cause huge problems. However, we are not done with what coders and winders need to know. Stay tuned for the next clip where we will talk about the coefficient of web-web friction, perhaps one of the most underappreciated of web properties.